Hey everybody, welcome back to chemistry. And so we are continuing on through the section in the gases chapter about the kinetic molecular theory. And so now I want to talk about two properties that gases have. And so they have the property of diffusion and they also have the property of effusion. And this can be found in section 7.11 of your book. So first off, let me talk about what diffusion is. And maybe you learned this sometime in the past. What diffusion is where molecules move from an area of high concentration to an area of low concentration. So to explain this, what I'm going to do is I'm going to use this very silly example here. Okay, so let's say your instructor SP is at home and he's at the kitchen. And so he pulls out a box of eggs and he has forgotten that the eggs have been sitting in the refrigerator for about 6 months. And so they're probably rotten inside, okay? Now let's say maybe 20 feet away from where he's located, he has a friend. And so maybe another 20 feet away from that, he has another friend. So the first friend that is closer we'll call friend A, and the second friend that is a little bit further away we'll call friend B. And so let's say that instructor SP decides that he's going to open up this box of rotten eggs. And so he opens up the box of rotten eggs, and what happens? And well, he gets a very bad smell, okay? And so the smell is due to a molecule called hydrogen sulfide. And so what happens is that when eggs get old, there's a little bit of sulfur in the eggs that combines with hydrogen from other molecules and produces H2S. The chemical name is dihydrogen monosulfide, but it's just colloquially called hydrogen sulfide. And so this is a very icky, foul-smelling gas. And so here are the hydrogen sulfide molecules here. And so let me just indicate here that one of these molecules is hydrogen sulfide. And so right after the egg box is open, those molecules are right over instructor SP. Well, you know what's going to happen. Maybe after a minute or two, the person, the friend, that is 20 feet, which is about 6 meters away, starts smelling the rotten eggs. And then maybe some more time elapses, maybe another minute or two passes, and then friend B starts smelling the hydrogen sulfide molecules, the rotten egg smell. So why does this happen? Well, this is due to a gas's propensity to move by diffusion from areas of high concentration to low concentration. So right over the eggs, we have this hydrogen sulfide gas over me in high concentration. So immediately after you open up the box of eggs, there are no molecules of hydrogen sulfide there. So they're in low concentration. So we're going to go move molecules from high concentration to relatively low concentration like this. And so now the hydrogen sulfide is over friend A, and friend A is pretty upset, okay? And so now maybe what happens, you wait a little bit more time, and so you know that friend B is going to smell the hydrogen sulfide molecules, and you know why. It's because over friend A, they're at relatively high concentration. Here at friend B, they're still at low concentration, but the molecules will diffuse to areas of lower concentration, and then friend B starts smelling the hydrogen sulfide molecules, and he's upset too. So what can we learn from this story? Well, one thing we can learn is that molecules move from high concentration to low concentration through the process of diffusion, and also for you to choose your friends carefully. Okay, now what I want to do is I want to talk a little bit about why things occur when they do. So there's something interesting going on here, and let me explain what that is. And so let's look at what we would predict that the speed of these hydrogen sulfide molecules are traveling at based on the knowledge you have of gases right now. And so maybe one of the things that you may recall is that the average speed of molecules, which is measured by a root mean squared average, is going to be equal to the square root of 3 times the gas constant R times the temperature in Kelvin divided by the molar mass. Now, what this basically means is we know the molar mass of the hydrogen sulfide molecules, which we do. We know approximately that it's going to be 34 grams per mole, and we know the temperature. Let's just assume it's at room temperature, and we know the value of R. We can calculate what the average speed of the hydrogen sulfide molecules. And so you can go ahead and do that for the average speed of hydrogen sulfide. And what you would get is if you plug in the numbers into the equation, I did this earlier, and I got 460 meters per second. Okay, so what is that in miles per hour? Well, in miles per hour, it's pretty fast. It's approximately 1,000 miles per hour. So that raises an interesting question, which is this: why is it that if these hydrogen sulfide molecules are traveling at 1,000 miles per hour, which they are, why is it that friend A and friend B don't have that smell immediately as soon as the box is open? So it's probably going to take a little bit of time, maybe a minute or so, for someone that is 20 feet or 6 meters away to smell these gas molecules. So these molecules are traveling at 1,000 miles per hour, but there's something maybe in the air that's preventing them from going that fast to get to the other people. So what is that? So we need to talk about that. Okay, so what I'm going to do is I'm just going to erase this silly picture here. I think it's done its job. Okay, and so let's just imagine what the hydrogen sulfide molecules should be doing. So this is what they should be doing. So here is your hydrogen sulfide molecule here, and it should be traveling at 1,000 miles per hour. And so this is how we imagine it going, right? Just in a straight path, going at 1,000 miles per hour. But in reality, this is the path that a hydrogen sulfide molecule is probably going to take. What's going to happen is it's going to go forward for a bit, but then boop, and then like that, and that, and that, and that, and that. And it just kind of bounces around in random directions like this, but it's slowly kind of going forward eventually. And so it's slowly going in the direction to lesser concentration. So the question is, why is the hydrogen sulfide molecule bouncing around like this? Well, you have to imagine that the hydrogen sulfide molecules are traveling through air, and air has molecules in it. It has mostly nitrogen molecules and oxygen molecules. And so the hydrogen sulfide molecules are going to strike other air molecules and bounce off them. And so that prevents the direct path of the hydrogen sulfide molecule through space. So we just have to sort of remind ourselves here that when you have some kind of gas like hydrogen sulfide is trying to pass through another gas, well, it's going to have to strike these other gas molecules, and that's what's going to effectively slow it down. So instead of maybe this gas molecule unobstructed going at 460 meters per second, it may be going at something like 4 meters per second after all these strikes for it to go forward. So in fact, what is going on is that when you have, say, hydrogen sulfide molecule passing through the air molecules, it is undergoing several billion collisions per second. And so the path it's able to take is going to be a very short one before it strikes another molecule. And so we call the length of the path that it takes before it strikes another molecule called the mean free path. So I have that in this slide here. And so here, say this distance here that it collides off one molecule and hits another one is called the mean free path. So the mean free path, as you might imagine for a gas molecule, is not going to be a very large length. In fact, say for a hydrogen sulfide molecule, the mean free path is about 100 nanometers in length, which is about 1/100,000th of a centimeter. So it's not very much. And so here, that's the way we sort of evaluate how fast things diffuse, is by understanding what the length of the mean free path is. Now, one thing you should imagine is that there are things that are going to affect the length of the mean free path. And so one thing that's going to affect it is the number of molecules that the gas is passing through. And so what we might imagine is that if there are more molecules in the space or more pressure, then the mean free path is going to be shortened because it's not going to take as much time before it strikes another molecule. On the other hand, if you remove molecules and you approach, say, a vacuum where there are very few molecules in the way here, the mean free path could be quite long. And so it may be, say, meters before it strikes another molecule. And so that will be all I'm going to say about diffusion. And so now what I want to do is talk a little bit about what effusion is. And so that will be on the next slide here. So you should know the difference between diffusion and effusion. So diffusion, spelled with a D, and so let me rewrite this on the board here. Diffusion is the measure of movement of molecules from areas of high concentration to low concentration. Effusion, which begins with an E, is slightly different. What effusion is the measure of the rate of molecules passing through an opening or a hole so that it can go into a vacuum. So that's sort of the official definition of effusion. But what I want to do before I start explaining fusion is I want to talk about a sort of a practical example of effusion. So here I have imagine I have two balloons and they're filled up with equal moles of gases. And so in the left balloon we have molecules of air, and so it's going to be mostly nitrogen but with some oxygen as well. And then in the right balloon we have the same number of moles, the same amount of gas, but this time it's helium. So the question is this: which balloon is going to deflate the fastest? Is it going to be the balloon with the air molecules, or is it going to be the balloon with the helium molecules? And so the way you sort of address that is with your knowledge of effusion. And so let me write out an equation that helps us understand what effusion is affected by. I'll bring up the next slide. So we have that equation there, and so let me write this here, in that the rate of effusion is going to be not equal to, but proportional to the square root of 1 over m, with m being the molar mass. So notice that we do not have an equal sign in this equation, and so we really can't say take a number for molar mass and calculate the rate of effusion. The only way we could do that is if there was an equal sign there. The only way we could put an equal sign here with this particular equation is it would have to look something like this. It'd be rate of effusion is equal to a constant, say k, times the square root of 1 over the molar mass, but we're not going to do those calculations in this class. And so what we really just want to understand here is the proportionality between the rate of effusion and the molar mass of the gas. Okay, so let's talk a little bit about that. So what I'm hoping you can see is that you can look at this equation and understand that the heavier that the molecule is, the greater and greater its mass, as reflected in its molar mass, then the rate of the effusion will be slower and slower. So let's imagine why that might be the case. Well, that might be the case because here we have molar mass in the denominator. So imagine what happens if this number in the denominator gets larger and larger and larger. Well, then what you can imagine is that here the rate of effusion, which is on the other side of the proportionality symbol, in the numerator is going to get smaller and smaller and smaller. So that predicts that when you have heavier and heavier gases trapped in some kind of container and they're trying to get through an opening or a hole, then the heavier gases is going to take more time for them to effuse. And that kind of makes sense if you think about it. So going to this balloon example here, so imagine that we're in the surface, or we're, say, looking inside the balloon here, and so let's say you had a super powerful microscope, and what you would probably see is that there are small openings or pores in the balloon. And so if you can sort of imagine that, then what is going to affect the rate of effusion? It's going to be the size of the molecule, in that if you have relatively light molecules, they'll be kind of small, and so they're going to be able to pass easily through these pores, and so the rate of effusion will be greater. But if you have heavier molecules, they're going to be larger, and so they're going to have a little bit more trouble getting through these pores, but they may eventually get out. And so that kind of helps us understand how we can sort of answer our question with the balloons. Which is going to deflate the fastest? Is it going to be the balloon filled with air, or is it going to be the balloon filled with helium? Well, again, just imagine that the surface of these balloons is made up of millions and millions and millions and millions of tiny pores. And so you have to imagine, well, which molecules are going to get through the fastest? Well, the ones that are going to get through the fastest are the ones that are going to be lighter molecules. Well, which ones are the lighter molecules? Well, nitrogen has a mass of 28 grams per mole. Oxygen has a mass of 32 grams per mole. Now compare that to helium. Helium has a mass of 4 grams per mole, so it's a much lighter atom. It should have a much easier time of passing through the pores of the balloon, and so we would predict that a helium balloon will deflate the fastest. Okay, so now one of the things you're probably going to have to do is you may have to solve a problem on your Achieve homework or your test that would be more quantitative in nature about the rate of effusion. So let me bring that up. But before I do that, here I have sort of another example of a qualitative question that may be asked of you, is can you predict which of those two molecules, nitrogen dioxide or iodine, would effuse out of a container faster? And so what I'm hoping you can do is figure out that the heavier of those two gases will effuse slower, and the lighter of those two gases will effuse faster. And so there is a calculation of the molar masses of the gases, and so you can see that because NO2 has the lower molar mass of the gas, it should be able to effuse the fastest. Okay, and so we're going to get to that quantitative problem in a minute, but to be able to solve the quantitative problem, what we need to do is understand what a formula is for solving quantitative problems with effusion. It's called Graham's law of effusion. So let me give you that formula. So the formula is this. You have the rate of a molecule. You can call it 1 if you want, or you can call it A. So we're going to call this rate A because we're referring to the rate of gas molecule A divided by the rate of gas molecule B. So it's going to be a different molecule B is going to be equal to the square root of the molar mass of gas B and then divided by the molar mass of gas A. And so now I kind of want to point out something very important here. Notice that on one side of the equal sign we are dividing rates. On the other side of the equal sign we are dividing molar masses, but then we would have to take the square root of that. But also notice the location of the types of gases on either side of the equal sign. And so on the left side, with the rates, we have the rate of a gas A in the numerator, but on the right side, that rate is going to be in the denominator. So notice the flip. So that kind of makes sense because we saw in general that the rate of effusion is going to be equal to the square root of 1 over the molar mass. And so we would expect that the rate of effusion of a particular gas A is going to be inversely proportional to the square root of the molar mass of that gas A. And the same thing is true here with B. It's just now they're taking different locations in the numerator and denominator. Okay, and so now what we can do is we can use this equation to solve problems that you might encounter. And so here's sort of a nice problem that we can do here. Okay, the problem reads as follows. An unknown gas has a rate of effusion that is 0.462 times that of nitrogen gas. What is the molar mass of the gas in grams per mole? Okay, and so we can go ahead and use this formula. So let's go ahead and try to assign variables to the best of our ability here. So it says an unknown gas has a rate of effusion that is 0.462 times that of nitrogen gas. Okay, and so it looks like we have a number associated with a rate of effusion. So that would not be the molar masses, at least yet. We're dealing here with rates here. Now, if you read that carefully, it's a proportionality between the unknown gas and the rate of nitrogen. Okay, so here's a way you can think about this. And so we have the rate of the A gas, we'll call it unknown, and the rate of the B gas, which is nitrogen. And so we are told that the rate of the unknown gas is 0.462 times the rate of the nitrogen gas. Now, this is just a number, and so it doesn't need units because it's just dividing a rate, say, in molecules per second by another rate, which is molecules in second. They canceled out and got what you got. And when you do that calculation is unitless. And so it's just going to be 0.462. So that will be good so far. Okay, now looks like we have to figure out the molar masses of gas B and gas A. So the molar mass of A is the molar mass of the unknown gas, and so that's what we're trying to find. And then we have the molar mass of B. We'll make that the molar mass of nitrogen. Okay, so you have to be careful when calculating the molar mass of nitrogen. And so it tells you that the nitrogen is nitrogen gas, and you have to remind yourself that when nitrogen is at room temperature and pressure in the gaseous state, is two atoms bound together, is diatomic. So you have to add up two atomic masses of nitrogen. And so when you do that, you get 28.02 grams per mole. Okay, so now what we can do is we can substitute numbers into the equation. So we have the rate of the unknown divided by the rate of N2. Let me rewrite this to make this a little bit clearer. So I'm going to write this over here. So it's going to be the rate, we're going to say A is the unknown, divided by rate of B. We're saying B is N2, is going to be equal to the square root of the molar mass of B, which is N2, divided by the molar mass of A. A is the unknown. Okay, so the next thing I want to do is make this problem a little bit easier by doing some manipulation here to get rid of the square root. And so the easiest thing to do is just to square both sides. So I'm going to square the right, and I'm also going to square the left. And so let's see what we get after we do that. And so we have the rate of the unknown gas over the rate of N2, and this will be squared, is going to be equal to, we're going to square the square root, so that simplifies things over here on the right side pretty much. So we have the molar mass of N2 divided by the molar mass of the unknown. Okay, so now what we can do is solve for the molar mass of the unknown. So the molar mass of the unknown is going to be equal to the molar mass of the N2 divided by the rate of the unknown divided by the rate of the N2, and this will be squared. And so what we can do is we can put in some numbers here. And so the molar mass of nitrogen gas is going to be 28.02 grams per mole. And you divide that by here, it looks like the relative rates of the unknown gas compared to N2, that's squared, so it's going to be 0.462, but you have to remember to square that. And as I recall, if you went ahead and did this math, what you would find for the molar mass of the unknown gas is going to be about 131 grams per mole. Okay, thank you for listening to this presentation. We'll see you next time.